orthonormal sets. So first of all, we will prove two lemmas related to orthogonal complement of a set. If Y is a closed subspace of a Hilbert space H, then Y is equal to double orthogonal complement of Y. We know that Y is a subset of double orthogonal complement of Y. So it is sufficient to show that Y double orthogonal complement of Y is a subset of Y, or Y contains double orthogonal complement of Y. We know that if A is a subset of B and B is a subset of A, then A is equal to B. Suppose X is any arbitrary element belonging to double complement of Y. It means that we can write X equal to Y plus Z, where Y belongs to Y, which is a subset of double orthogonal complement of Y. It means Y also belongs to double orthogonal complement of Y. Because double orthogonal complement of Y is a vector space and X belongs to it by assumption, so we have Z equal to X minus Y. Because X equal to Y plus Z, it means shift Y to this side, Z equal to X minus Y, and this belongs to double orthogonal complement of Y. Or we can say Z is orthogonal to orthogonal complement of Y. But this Z belongs to orthogonal complement of Y. So it means Z is orthogonal to Z, and it means Z is equal to 0. If Z is equal to 0 here, then X equal to Y. But Y belongs to Y, therefore X also belongs to Y, because X is equal to Y. So we have proved that if X is any arbitrary element of double orthogonal complement of Y, then it also belongs to Y. It means Y contains double orthogonal complement of Y. So combining this, that Y is a subset of double orthogonal complement of Y, and this we get Y is equal to double orthogonal complement of Y. Since orthogonal complement of Z is equal to double orthogonal complement of Y, which is Y as we have shown, we can write H equal to direct sum of Z and its orthogonal complement. So it means as X tends to Z, define a projection PZ of H onto Z. Here H is a Hilbert space whose properties are similar to those of projection. One more lemma: for any non-empty subset M of a Hilbert space H, the span of M is dense in H if and only if orthogonal complement of M is equal to singleton set 0. Now this lemma has two parts: that the span of M is dense in H if orthogonal complement of M is singleton set 0. Secondly, if orthogonal complement of M is singleton set 0, then the span of M is dense in H. So first we will assume that X belongs to orthogonal complement of M, and we denote V by span of M to be dense in H. It means this X belongs to closure of V, which is equal to H, because V is the span of M which is dense in H. So it means X belongs to this closure of V which is equal to H. Because closure contains all its limit point, therefore there is a sequence Xn in V such that Xn tends to X. But X belongs to orthogonal complement of M, and orthogonal complement of M is orthogonal to V. It means inner product of xn with x is equal to 0, because xn is a sequence in V. It means inner product of xn with x is equal to 0. But inner product is continuous. It means inner product of xn with x tends to inner product of x with x. But this inner product of x with x is norm of x square. Because this is 0, therefore this is also 0, and it means norm x equal to 0. It means x is equal to 0. So x was any element of orthogonal complement of M which is 0. It means orthogonal complement of M is singleton set 0. Now for the converse part, suppose orthogonal complement of M is equal to singleton set 0. If x is orthogonal to V, then x is also orthogonal to M, because V is span of M to be dense in H. And because x is orthogonal to M, it means x belongs to orthogonal complement of M. But orthogonal complement of M is singleton set 0. It means x is equal to 0. And therefore, orthogonal complement of V is also 0, because V is span M to be dense in H. And we note here that V is a subspace of H, therefore V bar is equal to H, means closure of V is equal to H, or we can say that the span of M is dense in H. Now orthonormal sets and sequences. We have seen that orthogonality of elements plays a basic role in inner product and Hilbert spaces. Of particular interest are sets whose elements are orthogonally in pairs. If we consider in Euclidean space R cube a set of 3 unit vectors E1, E2, E3 in the positive direction of rectangular coordinate system, then these vectors form a basis for R cube. These E1, E2, E3 form a basis for R cube. Therefore, any element x belonging to 3-dimensional real space has a unique representation, and we can write x equal to alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3. This is by definition of basis. Now we see a great advantage of orthogonality. Suppose we are given some x, we can readily determine the unknown coefficients alpha 1, alpha 2, alpha 3 by taking the inner products. In fact, to obtain alpha 1, we must multiply that representation of x by E1, means inner product of x with E1 will be equal to alpha 1 inner product of E1 with E1. I am taking this inner product. Inner product of x with E1 is equal to alpha 1 times inner product of E1 with E1, alpha 2 times inner product of E2 with E1, alpha 3 times inner product of E3 with E1, and so on. In more general inner product spaces, there are similar and other possibilities for the use of orthogonal and orthonormal sets and sequences. In fact, the application of such sets and sequences makes up substantial part of theory of inner product and Hilbert spaces. Here this is alpha 1 E1, this is alpha 2 E2, and this is alpha 3 E3. An orthogonal set M in an inner product space X is a subset of X whose elements are pairwise orthogonal. Now orthonormal sets. An orthonormal set M, which is a subset of X, is an orthogonal set whose elements have norm 1. That is, for all xy belonging to y, Inner product of x with y is equal to 0 if x is not equal to y and 1 if x equal to y, because its elements have norm 1. If an orthogonal or orthonormal set is countable, we can arrange it in a sequence xn and we call it an orthogonal or orthonormal sequence respectively. If it is orthogonal, then we call it orthogonal sequence. If it is orthonormal, we call it orthonormal sequence. Orthonormal set is also an orthogonal set, but the difference is its elements have norm 1. So, if we consider a family X alpha of indexing set where alpha belongs to I, then it is called orthogonal if X alpha is orthogonal to X beta for all alpha beta belonging to I and alpha not equal to beta. And this family is called the orthonormal if it is orthogonal and all X alpha have norm 1, because its norm of orthonormal sets have norm 1. So that for all alpha beta belonging to I, we have inner product of X alpha with X beta equal to 0 if alpha is not equal to beta and 1 if alpha is equal to beta. We also denote it by delta alpha beta, which is called Kronecker delta. So we shall consider some simple properties and example of orthogonal and orthonormal sets. For orthogonal element xy, we have inner product of xy equal to 0. So we obtain the Pythagorean relation norm x plus y whole square equal to norm x square plus norm y square. So this is norm x plus y, norm x, and this is norm y. If in place of two vectors we have n vectors x1, x2, xn, then this is an orthogonal set. Then norm x1 plus x2 plus xn whole square is equal to norm x1 square plus norm x2 square plus norm, and so on up to norm xn square. In fact, we know that inner product of xj with xk is equal to 0 if j is not equal to k. It means norm xj square, where the summation varies for all the j's, is equal to inner product of xj and xk. Here summation varies over j, here over k, and we can write it as, if we take summation outside, inner product of xj with xk, and if it varies only for j, then inner product of xj with xk can be equal to norm of xi whole square. Here it varies only on j. J varies from 1 to n. Means x1 square plus x2 norm x1 square plus norm x2 square plus norm xn square, and so on. An orthonormal set is linearly independent set. If E1 E2 be an orthonormal set and we consider the equation alpha 1 E1 plus alpha 2 E2 plus alpha n En equal to 0, then we know that it is linearly dependent if at least one of alpha is not equal to 0, and it is linearly independent if all the alphas are 0. Means alpha 1, alpha 2, alpha n are all 0, then we say that it is linearly independent. If we multiply it by Ej, then we get, I have written in short, means in summation form, alpha 1 E1 plus alpha 2 E2 plus alpha n En to be sigma alpha k Ek, where k varies from 1 to n, and its inner product with Ej gives alpha can be written outside. Alpha, this sigma and alpha can be shifted outside, and this is inner product of Ek with Ej, and this is equal to alpha j, inner product of Ej with Ej, and this is 0, therefore alpha j equal to 0, and this proves linear independence for any finite orthonormal set. This implies linear independence if the given orthonormal set is infinite by the definition of linear independence. For example, Euclidean space in Euclidean space R cube 3-dimensional. If it is 3-dimensional, the three unit vectors 1 0 0 0 1 0 0 0 1 in the direction of three axes of a rectangular coordinate system form an orthonormal system. Also in the space L square, an orthonormal sequence is En, where En is equal to delta Nj. It has the nth element 1 and all other elements 0. A great advantage of orthonormal sequence over arbitrary linearly independent sequence is the following. If you know that a given x can be represented as a linear combination of some elements of an orthonormal sequence, then the orthonormality makes the actual determination of the coefficients very easy. In fact, if E1, E2, En is orthonormal sequence in an inner product space X, then we have X belonging to span E1, E2, En, where n is fixed. Then by definition of the span, X is equal to inner product of xk, k equal to 1 to n, alpha k, ek. And if we take the inner product by a fixed ej, then it will be inner product of x with ej equal to, this is not here. Here x is equal to sigma k equal to 1 to n alpha k ek. If we take the inner product of a of a fixed ej, then we get inner product of x with ej equal to the sigma k equal to 1 to n alpha k ek with ej. If we take alphas out, then it will be sigma alpha k inner product of ek with ej, and this is nothing but alpha j. With these coefficients, x is equal to sigma k equal to 1 xk ek, inner product of xk ek and ek. Now Hilbert adjoint operator T star. If T is a mapping from a Hilbert space H1 to Hilbert space H2 is a bounded linear operator, then the Hilbert adjoint operator T star of T is the operator such that for all x belonging to H1 and all y belonging to H2, inner product of Tx with y is inner product of x with T star y. T star is the Hilbert adjoint operator of T. And a bounded linear operator T from H2 itself on a Hilbert space H is said to be self-adjoint if T star equal to T. If we write T star equal to T here, then we will get inner product of Tx with y to same as inner product of x with Ty. This self-adjoint operator is also called Hermitian operator. And this bounded linear operator T from H to H on a Hilbert space H is said to be unitary. If it is bijective, bijective means it is 1 1 as well as onto, and T star is equal to T inverse. And this operator is said to be normal if T star is equal to T star T. Here T star is Hilbert adjoint operator of T. So now we will prove one result. Let H be a complex Hilbert space if T belongs to BH, then there exist unique self-adjoint operators T1 and T2 such that T is equal to T1 plus iota T2. Here T1 and T2 are respectively called the real and imaginary parts of operator T. So we have to write that T can be expressed as T uniquely in terms of T equal to T1 plus iota T2. If we define T1 equal to 1 by 2 T plus T star and T2 equal to 1 upon 2 iota t minus t star, then clearly we see that t is equal to t1 plus iota t2. You can simplify and check it. Now we will prove that this t1 and t2 are self-adjoint. So t1 star is equal to 1 by 2 t plus t star of star. So because 1 by 2 is a real number, so we can take it outside, and t star, and this is t double star. T star means conjugate of t, t double star means conjugate of t. We know that if we take conjugate twice, we get the same number. So it means 1 upon 2 t star plus t. This is nothing but t1. It means t1 star is equal to t1. So t1 is self-adjoint. What about t2 star? If t2 star is equal to 1 upon 2 iota t minus t star whole star. Now, because iota is the imaginary number, its conjugate is minus iota. So here we will have minus 1 by 2 iota, and this t star, and t star of t star. This is t double star. If we multiply it by this minus inside, we will get 1 upon 2 iota minus t star, and this minus and this minus will become plus, and t double star is t, because conjugate of a complex number is also the same number. So this is equal to t2. So t2 star is also t2. It means t1 and t2 are self-adjoint. So we have expressed t as t1 plus iota t2, where t1 and t2 are self-adjoint. And this can be checked easily. You can show the calculation also by substituting the values. This t1 plus iota t2 comes out to be this t. Now we will prove the uniqueness part. Suppose if possible t is also equal to s1 plus iota s2, where s1 and s2 are also self-adjoint. It means t star is equal to s1 minus iota s2. Hence, if we add the two, 2s1 is equal to t plus t star. If we subtract the 2 iota s2, because s1 and s1 will cancel, this will become plus 2 iota s2 equal to t minus t star. So therefore, s1 is equal to 1 upon 2 t plus t star, and this is nothing but t1 from here, and s2 is equal to 1 upon 2 iota t minus t star, divide by 2 iota. So this is nothing but t2 from here, 1 upon 2 iota t minus t star. So it means this representation is unique. So we have proved that for any operator on the Hilbert space, there exists a unique self-adjoint operators t1 and t2 such that t is equal to t1 plus iota t2. Thank you.